Hello, this is the Enthalpies lab. Since we don't have class Monday because of Veterans Day, we won't meet in the lab, but you will still have an assignment to do. So enthalpy is the study of heat that is absorbed or given off in a chemical reaction, or enthalpy is the heat. Calorimetry, I guess, is the study of it. Anyway, it doesn't matter. Anytime a reaction occurs, heat is either absorbed or given off. So if heat is absorbed, we call it an endothermic reaction. If heat is given off, it's an exothermic reaction. And calorimetry is the study of that and the measurement of that heat. Make sure you read through all the background stuff in the lab manual. There's a chart here on heat capacity, table 1 actually, some specific heat capacities. Different substances have different heat capacities. So you put a certain amount of energy in, it would raise that substance a certain temperature, and it varies from one substance to another. There's gold, mercury, copper, and so on here. Water is on here 3 times because there's solid, liquid, and gas, water. The one you're going to be concerned with for this lab is the value for liquid water, which is 4.184. So if we were meeting in the lab, you would actually be doing experiments in a coffee cup calorimeter. So you have a coffee cup with a lid on it and a thermometer that goes down through a hole in the lid into the cup. You'd have a stir bar in there, and you would actually start a chemical reaction in there and check the change in temperature on the thermometer. Since we're not meeting, you can't do that, but I have put a file in the assignment tab in Canvas that has the data already in there. So the experimental data is already put in there, and you'll have to do the calculations. The formulas for all of your calculations are on page 215. And you've got equation 12, 13, 14, equation 8, 15, and 13 again, I guess. All of the I think all of them you need are right there on those 2 pages. I mean, on that 1 page. There's a couple on the previous page. Yeah, you will, in the post lab, you'll use those on the previous page as well. The first part of the procedure would have been calibration of your coffee cup calorimeter, but we actually skip that in lab anyway, and we just use the accepted value of the heat capacity of the coffee cup calorimeter, which is 37.5 joules, which doesn't make any sense to you right now probably, but it will once I explain the calculations. So in the first part, you would have had some water in the cup, and you'd have a stir bar in there. It would be on the stir plate. You'd have a thermometer in there. You'd let it sit for a couple of minutes for the temperature to stabilize, and you'd look at the thermometer and record the temperature. Then you would dump a salt in there, a pre-weighed aliquot of salt of some sort. Potassium nitrate was the first one. And what you would do is lift the lid of the coffee cup, dump the salt in there, and close the lid down and let it keep stirring, and you keep watching the thermometer. And you record the maximum change in temperature. The temperature could go up if it's an exothermic reaction, or it could go down if it's endothermic. But you would just watch the thermometer and record the maximum change in temperature. And then the difference between the initial temperature and the final temperature would give you your temperature change, which you need for your calculations. And then you also would repeat that another time with sodium carbonate as a salt. And then we have enthalpy of formation, which is you have a copper sulfate solution and you add ammonia to it. And that forms a copper ammonia complex. And that would also either absorb or give off heat. And the last one is an acid-base neutralization. So you have some sodium hydroxide in the coffee cup, and you measure the temperature, then you dump in some acid and measure the temperature change. So this was all about just the temperature change of the reaction and just getting a careful measurement of that change. Then you've got a bunch of calculations to do. So looking at the, actually, let me share my screen. Okay, here's the file that you have in the assignment tab in Canvas. This is your data sheet. Notice that here at the top where it says calibration, record the heat capacity of the calorimeter, we've already marked in 37.5 joules per degree C. That's the accepted value. Here's your potassium nitrate salt. They give you the specific heat capacity for this salt, which you will need. These two, for the salts, they give you the heat capacity right here. The rest of them, the liquids after this, you're going to use the heat capacity for water, 4.184. But I'll come back to that. So the mass of your salt is right here. So they weighed out the salt and, no, I'm sorry, that's the mass of the calorimeter first. Then they have the mass of calorimeter plus the water. Oh, okay. Yeah, and then you just have to subtract to get the mass of the water that's in there. And then you've got the mass of the salt that was weighed out on the balance. What are the moles of the salt? Well, you're going to have to look up the molar mass for potassium nitrate. And then just divide the mass by the molar mass and get the moles. What is the mass of the solution, the salt plus the water? Well, you just add together the mass of the salt and the mass of the water. What is the initial temperature? 22.0 degrees. What's the final temperature? 19.0 degrees. So you can see here the temperature went down. So you're going to have a negative value for your delta T. You subtract the initial temperature from the final temperature. And since the initial temperature was the larger value, you're going to have a negative number here. And Q of the calorimeter. How do we get that? Well, we go back to that page that I said had all the formulas on it, page 215. And we find equation 13 says Q of the calorimeter is equal to C of the calorimeter, which was the 37.5 times delta T. So whatever your delta T was, and if it's negative, you keep it negative, you just multiply that by the C of the calorimeter, 37.5, and that gives you Q of the calorimeter. What is Q of the solution? Well, again, page 215, it tells you Q of the solution is equal to C of the solution, the specific heat, which in the case of potassium nitrate is the 4.085, times the mass of the solution, which you have right here on line 3, mass of the solution, times delta T, which is right here. So just multiply them together and get Q of the solution. And it's kind of split in this file for some reason. Q of the reaction, line 7. Go back to page 215, and we see that equation 8 says 0 is equal to Q of the reaction plus Q of the solution plus Q of the calorimeter. Well, just bring Q of the reaction to one side there, bring that over in place of the 0 there. It'll become a negative when you bring it over to the left of the equal sign. And then add the other two together, the Q of the solution and Q of the calorimeter, and change the sign. If it's negative, make it a positive, and if it's positive, make it negative. And that gives you your Q of the reaction. Line 8 says delta heat of the reaction is equal to Q of the reaction divided by the mass of the salt. So very simple, just divide it by the mass of the salt. And then line 9 is Q of the reaction divided by moles of the salt. So just divide that by the moles of the salt and put the answer there. And then the same series of calculations for the other salt, sodium carbonate. And the next one, people make a lot of errors here with this in determining the volume of the solution especially. But first of all, you've got to get moles of each thing. So they tell you right here, you have copper sulfate solution. It's a 0.5 molar solution, and you're using 25 milliliters of it. How do you get moles from that? Liters times molarity equals moles. So convert from milliliters to liters, multiply it by the molarity, and get the moles. You're going to do the same thing for the ammonia solution. The ammonia is 6 molar, and you use 25 milliliters of it. Liters times molarity equals moles. They measured the temperature differently for the two solutions. One was 21.0 degrees, one was 20.0. They want you to put the average temperature. So take the average of those two numbers. And then the temperature final, after they mixed them together, the temperature was 26 degrees. So calculate your delta T. Subtract the average T here from the final T and get your delta T. What is the mass of the solution? They tell you mass is equal to density times volume, and they tell you the density is 1.01. What is the volume of the solution? People want to put 25 milliliters here, but that's not correct. What did you do? You dumped these two together to make one solution. So what's the volume of the solution really? And get the mass of the solution. Then the rest of it is just going back to those equations again on page 215. Q of the calorimeter, Q of the solution, Q of the reaction, moles of limiting reagent. Remember the limiting reagent lab? You've got to look at your balanced equation and they give you a line to put the balanced equation there in your data sheet. Make sure you write in the balanced equation. It's in the background reading in your lab manual. So make sure you find that in there. Look at the balanced reaction, figure out your limiting reagent, and then you can answer that question there. What are the moles of the limiting reagent? And what are the moles of the complex that are formed? Well, again, look at your balanced equation. and refer back to the limiting reactant lab if you need to. And then finally, delta H of the reaction is Q divided by the moles of the complex formed. Then you have enthalpy of neutralization, very similar. Liters times molarity equals moles for the acid, for the base. Get the average initial temperature, they give you the final temperature, calculate your delta T. Mass of the solution, again, you dump the acid and base together to make the total solution, so add them up. Q of the calorimeter, Q of the solution, Q of the reaction, moles of limiting reagent, again. Moles of the water that's formed, so you neutralize an acid with a base or vice versa, you get water. And again, delta H of the reaction is Q divided by the moles of the water that's formed. Make sure you show all of your calculations. You have to show your calculations to get credit for this. And make sure that they're neat and organized so I can actually read them. You also have to do the some of the post-lab questions. I want to talk about post-lab number 6. It says a 12.99 gram sample of copper that is at 7.9 degrees C is added to 1 gram of hot water that's initially at 95.2 degrees C. So what's going to happen here? You drop this cold piece of copper into the warm water. And after it sits there for a little while, they're going to be at the same temperature. The copper is going to get warmer. The water is going to get cooler until they get to the same temperature. And you have to determine what that final temperature is. If we look back at page, where is it here? Okay. There is a place in here where it tells you that, well, let me just say, energy can't be created or destroyed. So what's happening here is we're transferring heat from the copper to the water. And the heat that is lost, no, I'm sorry, the heat that is gained by the copper is the same amount of heat that was lost by the water. So what we can say is that the copper is getting warmer. So we'll say Q of the copper, the heat gained by the copper is equal to negative Q of the water. And they also tell us, I'm looking at equation 6, Q is equal to mass times specific heat times delta T. So what you're going to use there is you're going to say the mass times the specific heat times the delta T of the copper is equal to the negative of the mass times the specific heat times the delta T of the water. And in our table here, table 1, we have right here copper specific heat is 0.385. And the specific heat for water is 4.184. So we can plug all these in then. We can say that the mass of the copper is 12.99 grams. So 12.99 grams of copper times 0.385, the specific heat of the copper, times delta T of the copper. We don't know delta T, but what we can do here is we can put the delta T is equal to T final minus T initial. We don't know T final yet, but what we can do is write T final minus 7.9 degrees C, which was the T initial for the copper. Then we've got an equal sign. Then we have a negative in parentheses because everything's going to be have a negative sign in front of it. Or the whole thing is going to have a negative in front of it. So put a negative and then parentheses. Then we had 1 gram of water times 4.184, the specific heat of water, times T final minus 93.2 degrees C, the initial heat of the water. Now our only variable is T final. And you've got to do some algebra here, but you should be able to solve that problem now. And that is it for this one. As always, let me know if you have questions. Send me an email or come to office hours. I can do a Zoom meeting if needed. That's it for now.